Hello my dear students, welcome back. In the previous class we discussed about the ampere circuit law, how it will be in the straight line conductor. So what will be the magnetic field due to a infinite straight conductor by using an ampere circuit law we have identified. Let us do the small recap of it. So when I am considering a long finite, here we should consider first an ampere loop with a radius r. Okay, we should consider an ampere loop for it. It's very important. Your magnetic field will be around this. Okay. After this, what I took the formula, that is B dot dl is equals to mu naught I. This is what your ampere formula. It's very important. Whatever you are considering in the ampere circuit law, the loop is very important. Amperian loop we will consider. That should be symmetry. Even here it is R. Okay. That's again an important point. Then I will apply the ampere circuit law, that is integration of B dot dl is equals to mu naught I. Fine. After this, what we should do? We are going to do an integration for the dl. Before that, it's a dot product. We want to know what is the angle made between them. What is the angle between them? So if this is magnetic field is here, my loop is here, both are in the same direction, my dl also is like this and my b is also in the, both are in the same direction. When both are moving in the same direction, the angle made between them is 0. Correct? That is integration of b dl cos theta is equals to mu naught I, because it's a dot product. What is the theta here? Integration of b dl cos 0 is 1 mu naught I. How I have considered the loop? I considered the loop in a circular manner. So b is integration of dl is equals to mu naught I. That is b integration of dl is what? 2 pi. What is the radius? Small r is equals to mu naught I. Now what will be your b? b is equals to mu naught I divided by 2 pi r. Same expression we got by doing the infinite straight conductor by using the Biot-Savart's law. There it was a complex problem because we did a long derivation. First we identified for the finite conductor, later on we have put it the phi 1 value, phi 2 value over there. So that long procedure is making a complex thing, but here complex also we can make such a simple thing by using an Ampere's circuit law. This is what we have learnt in the previous class. Today again it's very important, including for your board examination, it's very important. Today my topic is, here we did for straight conductor. Today we will derive expression for magnetic field due to solenoid. So you have heard this word, correct? No, solenoid, already you have heard this word. I will teach you now once again what is this solenoid. Okay, what magnetic field due to solenoid, we need to derive an expression for it by Ampere's circuit law. Ampere's circuit law. Okay. Now, first of all, what is solenoid? Solenoid is nothing but, see, if you consider the cylindrical coil or a conductor, there is an insulating of n number of turns. That is nothing but your solenoid. When I insulate the solenoid, by a copper wire, I am insulating by the wire by doing n number of turns to a cylindrical coil, that is nothing but solenoid. So let me write a definition for that. Solenoid is nothing but in cylindrical coil, by number of turns by n number of turns, okay, by large number of turns you can write, okay, better, large number of turns is insulated by a wire, even you can say copper wire or a wire, that is nothing but a solenoid. We all studied that in your 10th class, correct? There will be a cylindrical. So here if I connect to the battery, there magnetic field is produced, means current I is passing. Here how you should consider the current I means, the current I will go here, it goes here, okay, if I am starting like this, okay, here it is going inside, let me show the symbol like this. Here current is going inside and here current is coming outside. Here current is going inside, here current is coming outside. Current is going inside, current is coming outside. Inside, outside, inside, outside. What exactly? See something like this. When you want to threading, you have seen, no, they will put all the embroidery designs. They will put the needle like this and they will take out like this. They will put the needle like this, they will take out like this. So current is also going inside and it will come, inside and it will come. Like this the insulating wire, how the current is going to pass. Fine, the current is passing. If the current is passing, obviously no doubt there will be a magnetic field. Okay, how will be the magnetic field? So let me write for one coil like this. Let us consider for one coil how will be the magnetic field. So the current is going inside here. So my loop will be like this, and here outside, here it is inside, here it is outside. So my magnetic field will be like this. This is for one turn. Fine. If I consider for the another turn, what happens here? Please note here. Your magnetic field goes straight here, then it makes a loop. It goes straight here, then it makes a loop. Is that clear? Fine. Again, when you consider here another loop, what it happens? Again, your magnetic field goes straight here and make a loop, make a curved path. Again, it goes straight and make a curved path. What you want to understand? See, once again I am telling, for one coil it just makes like this. If another coil, it goes straight, then it makes a curve, then it makes a curve. For another coil again it goes straight and make a curve, it goes straight and make. So it's very clear, inside this there is a straight magnetic field. Maybe outside is like this, curved. Outside it is, maybe it is a curve like this, but inside it is a straight. Inside it is straight. Okay, this it should be clear. Fine. This is just for your understanding purpose. I will just erase this. Okay, outside there will be a magnetic fields like this, but inside it is straight. Fine. Okay. Now how to derive the expression? First, let me consider a loop for it. Let me write a clear view of the solenoid. So let me write the clear view of it. Okay. So let me consider the coil, current, cylindrical coil. Here current is coming out. Okay. Here current is going inside. So your loop is like this. Okay. Fine. It is understood that if we give the current only, it is passing and you will get the magnetic field. Inside there is a magnetic field is straight. What is my job? I want to find the magnetic field due to the solenoid. So think the point somewhere, the point P. This point is a solenoid. Due to the solenoid we are finding a magnetic field. Okay. So the first thing what you want to do, you need to consider a loop, Amperian loop. So here let me consider an Amperian loop. A, B, C, D. What is my first job? To consider the Amperian loop. So I have written A, B, C, D. I have considered the Amperian loop. And second, my job is what? To to write the Amperian circuit formula. That is integration, line integration of B dot dl is equals to mu naught I. We are not taking just I, we are considering net I. Okay, and we are not considering only for one particular point, we are considering a complete loop. So what is a complete loop? A, B, C, D is a complete loop. A, B, C, it is a complete loop. Let me take this as equation 1. Okay, before going to solve it, it's very clear that we are not having a complete loop to identify in a one time. We should make a division because we have A, B, C, D. So what I should do? I should divide separately. I should integrate it separately. So I'll integrate it. Fine. Integration of A to B I'll do first. A to B dot dl. Okay. Plus integration of B to C I will take. B to C, B dot dl. Next, integration of C to D, B dot, line integration of B dot dl, plus integration of D to A, B dot dl. Okay, this is your left part. This is equals to mu naught net I. First I will consider the net I. What to write the net? Where I should consider the net current. To consider the net current, what is my first job? See here, I am going to write. Think, first it's an example. Think I have n number of turns, that is I have 2000 number of turns. Okay, I have 2000 number of turns in the solenoid. Okay, what is my length of the solenoid? Length of the solenoid is 200 meters. For 200 meters, I have 2000 turns. For 200 meters, I have 2000 turns. Fine. For 1 meter, what is my turn? So what I will do? N is equals to 2000 divided by 200. Cancel. 2 ones are 10s are, n is equals to 10. So if I want to know what is a unit, per unit length turn means, I am doing like this, n is equals to capital N divided by L. If I want to know what is the n value, what I can do? N is equals to per unit how many number of turns I have into particular length. If I do, then I will come to know what is the net, how many number of turns we have in a solenoid, is it or not? Therefore, or else I give the example like this, I have 2000 rupees cost chocolate. 2000 rupees cost chocolate. In that 2000 rupees of chocolate, I have 200 chocolates. Cost is 2000 rupees. In that how many chocolates I have? 200 chocolates I have. For one chocolate how much it is? 10 rupees. Is it or not? So for one chocolate into how many number of chocolates I have, if I multiply one chocolate cost into how many number of chocolates, if I multiply, I will come to know what is the cost of my chocolate. Is that clear? So here how to write the net current means, before that make a note like this, N is per unit, N is per unit length. Okay, N is a per unit length of turn, N is the number of turn for per unit length. So the number of turns in solenoid, How I am going to write the number of turns in solenoid? That is N into L. Number of turns in the solenoid, N into L. Okay. Therefore, the net current is not passing only through this, complete turn it is passing. So, I into N into L. Okay. This is what the net current value. Okay. I will substitute in the net current value at the end, but make note of this. Net current value, take this as equation 2 and substitute that at the end. Okay. Equation 2. Fine. Now, we will do separately for all integration. A to B, B dot dl. See my dears, if you consider a loop AB, and my magnetic field also in this direction, AB direction also was like this, is it or not? So, what is the angle made between them? Theta is equals to 0. If theta is 0, what I can write? Line integration of A to B, B dl cos theta, okay, B dl cos theta. So, theta is equals to 0. So, it becomes line integral of AB, B dl into 1. Okay. Next, I will write line integral of B to C, where B dl. B to C means like this. My magnetic field is like this, B to C is like this. What is the angle made? 90 degree. So, theta is equals to 90. Correct? When theta is equals to 90, so what it becomes? B to C, B dl cos 90 is 0. Therefore, this term completely becomes 0. Again, when you consider C to D, here is your magnetic field, C to D is out of the plane. C to D is out of the plane of the magnetic field. I want to identify point was here, P is here. From the P it is out of the plane. Correct? So, when you consider C to D, B dot dl, I can say B is only equals to 0 due to out of plane. Okay. Next, let me consider D to A, B dot dl. D to A means again what? This is 90 degree. This angle theta is 90. So, theta is equals to 90. Again, we know that integral of D to A, B dot dl becomes 0 because cos 90 is 0. This becomes 0. So, what about the complete? This, everything is 0. What happens to this equation? This is 0, this is 0, this is 0. What happens to this equation? B dot, so in equation 1, okay, you just substitute this. In equation 1, we got the value of this, everything became 0. Only this value, that is nothing but A, B dot dl, okay, is equals to mu naught. From equation 2 I got, what equation 2 what I got? Net current is INL. So, this is only I got this much, fine. So, I will integrate the dl. We know it is in the straight line, correct? No, mu naught INL, it is a straight line. So, I will get only L, BL is equals to mu naught INL. This L will get cancelled. Therefore, B is equals to mu naught IN. So, this is what the expression mu naught IN. Once again I am explaining clearly. See here, first I took the solenoid, The current is going inside, outside, inside, outside. Outside you may have this magnetic field, but inside the magnetic field I am considering it is a straight line. So inside at one particular point P magnetic field I want to identify. So what I made, first initially I took the loop. Loop is ABCD is a loop, Amperian loop. After considering the Amperian loop, I wrote the Ampere circuit law. Integration of B dot dl is equals to mu naught net I. Okay. After that, integration is for a loop. A, B, C, D I cannot consider because it is a rectangle. At a time I cannot consider. I divided into 4 parts, A to B, B to C, C to D, D to A. So I took, after that I want to know what is the net value of the current I. So for that I took this formula, N is equals to NL. I hope so it's clear. Total number of solenoid turns I can identify by number of turns per unit length into length. If I do it, I will come to know what is my net number of current which is passing. We can identify by what? INL. Okay. I got in that net I value, fine. Now I want to get this value, so I want to make a different things. For AB I did, so angle you came to know both are in the same direction, theta is 0, done. After that B to C, when I am considering the angle made is 90 degree, cos 90 is 0, therefore it is 0. Okay. Again I will consider C to D, maybe the angle is not 90 but it is out of the plane. When it is out of the plane, magnetic field becomes 0. So this becomes 0, B only 0. Next again when you come back to D to A, the angle made is 90. When angle made is 90, this becomes again 0. Only in 4 terms we have only one thing that I considered. After that I will do integration for DL, that is nothing but L, it is not in a circular, do not write 2 pi r, it is L, okay, length L. So DL I will just consider L. This L and this L get cancelled, B is equals to mu naught I N. So how the solenoid magnetic fields, everything will be there. There is an animation video, go through that and try to imagine the magnetic fields in the solenoid, how it will be existed. Okay, fine. So this derivation again it's very important, please practice, it's very simple and try to see the videos 3-4 times a day itself, and if you are not able to understand, and you can call if you are not able to understand at any point, you can clear your doubts, fine. Now you go to the animation video. Here you can see the solenoid, how is your magnetic shape in the solenoid, and solenoid and its property, let me study. See, if you consider the wire, insulated wire, see in the helical path how you are seeing it is insulated, so that we will consider in the circular coil, cylindrical coil. When we connect a battery, current will be passing. See inside I said it is going straight. How it is going, just see there, it will go straight and it makes a loop, it goes straight and makes a loop. So it's just acting like a bar magnet, something like a south pole and north pole. See inside how it is going straight, you need to understand, and it comes to the south and north pole, it's acting like a bar magnet. When you are considering a north pole, how you will consider a north pole? When it moves anti-clockwise direction, we will consider in how the anti-clockwise direction we will write, like that we will take it as a north pole. When you consider for other side, okay, that is nothing but a clockwise direction. In the clockwise direction, according to the clockwise if I move it, there you can represent the south pole. So it is very clear that it is acting like a bar magnet, and how the lines is existed inside, and you have observed how it is passing clearly in this animation, is it or not? So now let us study the strength of a magnetic field inside the solenoid. The strength of the magnetic is directly proportional to the current, that is for sure, we have did the derivations too. Strength of magnetic field is proportional to number of turns per unit length. I thought you correct, and now we are taking N divided by L, and even it depends on the So it depends on both N and I. Thank you. I hope so you have understood the animation video. Okay, in the next class we will be discussing another important derivation. Thank you all. Have a nice day.